We continue review calculus 2. For the next questions, we will look at numerical integration. So we have the midpoint, the trapezoid, and the Simpson rule. Right, let's look at this example. The first one is the midpoint rule. We go from -1 to 1 and n equal to 4. So n equal to 4, so basically we just divide to 4 equal segment, and we go from -1 to 1. Right, first we'll determine the delta x, the width of a sub-interval b minus a over n. From -1 to 1, so we take 1 minus -1 divided by n is 4, so that is going to be 2 over 4, 0.5. So with that, we have from -1 to 1, the increment is 0.5, so negative 0.5, 0, 0.5, and 1. Now the midpoint is we're going to take the midpoint of each. And the midpoint is the average of this -1 and -0.5, so -0.75 and -0.25, 0.25, and then 0.75. Right, so we evaluated those points will give us the height, and then the width is 0.5. So if we're going to write this integral is approximately equal to the function that's 75.75 times delta x, the function at -0.25 delta x, the function at 0.25 delta x, and the function at 0.75 delta x. And if we factor out the delta x, we have the sum of this function at this point and then times delta x. Right, so that's why we write the math. Now, in terms of calculator, if we put this in the calculator, first we'll start all of this point into a list. So onto this one, and most importantly, we need to write the function. That is y1 -3 e to the 3x. So need to type that first before we type a list, and then we add all of those function values and then multiply by delta x. Yeah, so that is the midpoint rule. So then we will add all of the function values and then times delta x, which is 0.5. Right. As always, the first thing is enter the function -3 e to the -3x. I'm sorry, positive 3x. Right. So we have the function. Negative is this point, not the subtract sign. Right. Second mode, quick. Now we're just going to enter this second parentheses, -0.75, -0.25, 0.25, and 0.75. close the curly bracket, and then store into second and 1 for this one. Right, and now we just add all of them up. Second stat, go to number math, option number 5. Right, second stat, go to math, option number 5. And now we add the values. So we need y1 variable, y variable function y1, and evaluate at the list one, all of that, and then we multiply by delta x. That gives us negative 18.27. So we use a calculator and we have negative 18. Yeah, usually on the test I'm not really very picky with the decimal places, but 3 or 4 decimal places will be good enough. Right, now as always when you do this with the definite integral, it's good that we check to see what the answer is supposed to be. If it's close enough, then it will be good enough. Right, so yeah, right, so that's good enough. It's not something like completely off. Of course, depends on the function. E to the 3x, that function is exponential function, so that e to the 3, what is e cubed? When x equal to 1 to negative 1, so that is about this much. So the function is increased very much. So the rectangles evaluation using rectangle to estimate, it may not be the good way. So that's why the error. So that's good enough. So that's why it's good. Right, timestamp. Next, we go to the trapezoid rule. And with this one, we have n equal to 4 from 0 to 2. So again, we divide to 4 equal segments. 1, 2, 3, and 4. Go from 0 to 2. Right, the increment will be 0.5, 1, and 1.5. Right, the difference in the trapezoid rule is that the coefficient though is going to be 1, 2, 2 in the middle, and then 1 at the end. So if we want to estimate, we will factor out delta x divided by 2. So we're going to have the coefficient times the value at this point. And then in the trapezoid rule, it is delta x divided by 2. Right, so we just do that. Now if we want to use the calculator, we store this into list 1, this into list 2, and then the rule is we have y1 list. It doesn't matter. This one is the list 2. Okay, let's this be the list 2, and the values is list 1. So we evaluate the function at this point, and then times the coefficient would be list 2, and then times delta x divided by 2. But first, of course, the function is ax squared ax squared, right? Now, oops, sorry, store. Okay, of course we can just use the bracket to store the numbers 0, 0.5, like that. Another way to do this is hit stat and then enter. Now you see there's the numbers here, right? If we want to clear, highlight it, hit clear and enter. Never delete a list, because if you happen to delete one of them, it will disappear. In that case, we have to name it again. And I don't know how to move the L5 in between here. So in that case, you have to delete everything and then name again L1, L2, L3 in that order if we mess up. So do not delete a list, only clear a list. Right. Now, L1, I will enter the number. In here, we can just use the enter. So that is maybe a better way to enter numbers. It's easy to keep track with. And then L2, the coefficient 1, 2, 2, 2, and 1. You see the coefficient match between this one, these two match perfectly. So there's a better way. Just hit stat, edit, and then we enter the numbers. Right, so that's what we have. Now, we have y1, right? Then we just need this second stat, go to sum, and then variable, y variable, function y1, evaluate at list 1 times list 2 times delta x 0.5 divided by 2. By the way, I didn't actually find it, but delta x from 0 to 2 divided by 4, so that again 0.5. So we have 22. Now, like I said, as always, good to do that by hand. I mean, of course, we can do that by hand too, but we can use a calculator. X squared. Right, so this one close enough. Right, next, we do that, but we have n equal to 4 all the time. Why don't we change it? Let's say this time we use n equal to 5. Right, it makes several change like that. Right, also trapezoid rule when n equal to 5. So we have that interval divide them into 5 equal segments. 1, 2, 3, 4. 2, 3, 4, 5, right. We go from 1 to 5. Right, delta x, the width of a sub-interval. Oh. Forgot timestamp on the other one. Is equal to b minus 8 over n. 5 minus 1 over 4. I mean n is 5 this time. I just want to change so we have different numbers. So 4 over 5 is 0.8. So 1, 1.8, 2.6, 3.4, 4.2, and then 5, right? So this will be L1. L2 will be the coefficient. The h will be 1, everything in the middle we have 2, and the rule is that. But most importantly, first step we do is enter the function, because this will be L2. So function 1 divided by x squared. If you're not comfortable with that, maybe we choose just 1 divided by x squared in the parentheses. So that definitely x squared at the bottom. Alright, so we have y1, check. Now as for the list, we can enter like this. I think it's better just hit stat, edit, and then just enter the numbers like this. Or you can clear, or we can just enter the numbers on top of it. I usually highlight it, clear, and enter. Now it's better to enter the numbers like this. And now we see that I just need to change one subtle change, right? So that's coefficient. Okay, good. And now of course we can enter again second stat, some variable, y variable, function y1, evaluate at list 1 times list 2 times delta x divided by 2. Right, of course you can do that. That's what we have. Or if we get lazy, we just copy what we have earlier. That's still the same thing for the trapezoid rule. Okay, we have that. Now let's check. Go from 1 to 5. And 1 over x squared. And that gives us, yeah, close enough answer. So let me write this again. Summation of y1 L1 times L2 delta x divided by 2. So that's the trapezoid rule. Right, next we have the Simpson rule. Simpson rule, the coefficient will be 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Delta x divided by 3. Right. So n equal to 4, so we divide this into 4 equal segments. Right, we go from 0 to 2, divide to 4 segments. So first delta x is b minus a over n. So we go from 0 to 2. Increment is 0.5. So that will go to list 1. The coefficient corresponding to Simpson's rule is 1 at the end, and then in the middle 4, 2, 4. It's always 4, 2, and 4, 2, 4, 2, and at the end going to end up with 4, 1. It starts with 1, 4. So this will only work when n is even number. If n is an odd number, we cannot have end up with a 4. Right. So this will go to the coefficient L2, and I will do the same thing except delta x divided by 3. If we want to write out the integral approximately equal to, we have 1 I mean f of 1, sorry, the coefficient is 1 times f of 0, 4 times f of 0.5, and then 2 f of 1, and then 4 f of 1.5, and then 1 of f of 2. Add all of them up, multiply by delta x divided by 3. So in the calculator we will have summation of y1, this one, multiply L2 times delta x divided by 3. Make sure the function is ax squared. I should just hit clear from the beginning. Ax squared, sorry. Right, quick. Start the function. Right, now this time I'm just going to store instead 0, 0.5, 1, 1.5, and 2. Close that, store into list 1. List 2 is the coefficient 1, 4, 2, 4, and 1. Close that and store into L2. If you want to check, hit stat, edit. Now we see those are the lists. Now the nice thing is when we do the store like this, it doesn't matter what we have earlier. Like the list earlier have 5 elements. When we do something completely new, store into it, it will have something new values. So if you want to enter something on top of this, you have to clear the list. You cannot just enter the original. If it is like this, we have to clear it and enter again. Of course, we can delete just one number. You can delete a number, don't delete a list. Right, so we have that, which is good. Second mode, too quick. And then the Simpson rule. Stat, go to summation. Sorry. You can, on the sum calculator, you can just hit alpha 3 to go to y1. Of course, variable here can get you to y1 as well. To L1 times L2 times delta x divided by 3. I have that, and because earlier we did say that it is about 21.33. So the Simpson rule here get the actual answer, right? You say, why do we have the perfect answer here? Well, the reason is the Simpson rule use quadratic to fit the curve. So the second degree polynomial to fit the curve, and we have the second degree here. So the curve will fit perfectly. So that's why this answer should get the exact answer. Right, 21.33. Yeah. That's what we have. Right. Next we have improper integral. So improper integral, an integral is improper due to 2 reasons. By the way, there's no more. We don't have any formula for that. Just integral rules. Right. So two reasons that make this an improper integral. The first one is obvious, where we have negative infinity or infinity on the limit. The second one is a little less subtle. Is if you put something in there and make it undefined. So that will be a problem, right? So from negative infinity to 0, and so if we put all the negative numbers in here, it's going to be negative square, so it's still negative. Bottom line is we don't divide by 0, so this is okay. If we have negative infinity to 5, for instance, that will be a big problem, because if we put 1 in here, it's undefined. So anything except for 1, it should be okay, right? So this one is different than this one is defined when we don't have to deal with 1, right? So good. Just go straight from there, and the first thing we'll see is the negative infinity. That is at the lower limit. So we say we use a for the lower limit. Right, let's say a goes to negative infinity, and now the integral, we go from a to 0. Yeah, that make it improper. Right. Now next, this integrate, just a simple substitution. That will be x minus 1. We can take derivative, move the dx, and then also the limits. When x equal to 0, u is equal to what? 0 minus 1. When x equal to a, u is equal to x minus 1, so a minus 1. Right. Now we have the substitution. First of all, still the limit though. Now the limit will change from a minus 1 to negative 1. And we have 17 over u square, and dx is du. But I can take the 17. The 17 is on the top. Let's put that on the top. A minus 1 minus 1 1 over u square, so make it u to negative 2. Right, the integral of u to negative 2 is u to the negative 1 over negative 1. Right, increase power by 1, divide by the same thing. Evaluate from a minus 1 to negative 1. Right, let's rewrite this a little bit. 17 divided by negative 1 is negative 17, and then u to negative 1 move to the bottom, so we have negative 17 divided by u. We go from a minus 1 to negative 1. Right, now we can substitute in 1. Negative 17 over u. Right, subtract negative 17 divided by a minus 1. Right, now take a look. This one obviously is 17. That's the limit. Negative, that's a plus 17 over a minus 1. Now a goes to negative infinity, a minus 1. So negative infinity minus 1 is still negative infinity. A finite number divided by infinity. So this one will go to 0. So this is equal to 17. Right. Sometimes it might help if we just evaluate maybe from a very negative number like this. And now 17 divided by x minus 1 square. Right. Yeah, that closes up to that 17. Right. Next we have that. Okay. So we write a little bit. I will take out the 2 and move the dx on the back. Right. You probably know that this is a substitution, trig substitution. This is 6 squared plus x squared. So x is going to be 6 tangent of theta. Or we just say what we're looking at is this one. Right, so I rewrite a little bit. But first, of course, take care of the limit. To make it a proper integral, the upper limit, so let's use b for it. And there's a 2, and then we can go from 0 to b. Now we write 6 squared plus x squared dx. Right, so that is 1 over a, which is 1 over 6. One over a. Let me zoom in a little bit. Tangent inverse of u over a, x over 6. Plus c, but we'll evaluate from 0 to b. That is 1 over 3 tangent inverse now we substitute b into it. 1 over 3 tangent inverse of x over 6 b over 6 subtract 1/3 tangent inverse of 0 over 6. Right. Now what is the graph of the tangent inverse? Tangent inverse of x. Alright, so it is like that. So if we're going to sketch, what is the graph of tangent inverse? Right, at 0, this is 0, tangent inverse of 0 is 0. And now this is tangent inverse of infinity, b go to infinity. Tangent inverse of infinity is pi over 2. Of course, that's, 1 over pi over 2 does not include in the 1 over 3. So we have 1 over 3 times pi over 2. And that's pi over 6. Right, so it's always good to evaluate this by hand. I mean, use a calculator to confirm our answer. X squared right, is that pi over 6? You know pi is 3.14 to divide by 6, so it's about that. That's so good enough. Forgot the timestamp. Right, next we have this one. So once again, obviously the problem is with the limit function here is always defined. Right, I forgot to mention one thing, that 36 plus x squared here, x squared is always greater than or equal to 0, so the bottom will never be 0. So we don't have any problem with undefined integral. Okay, talk about forgetting things. If we go back to problem number 36, just one thing that the answer might look differently. We have 1 over 36 here times 2 will be 1 over 18. So bottom line is, if in our answer we have a constant, we can just take it out completely because we have the constant at the end. So we can just say the 2 times 1 over 36 here is to a constant. So actually we have the 2 here, we can just take it out. If it is a constant in the answer, we can just take it out. And because we have the constant here in general already, right? Yeah, I forgot to mention that on that problem. But of course, it's not wrong to have a 2 there. Right, now we're back to this one. Right, so the function here is defined everywhere. So the only problem is the limit. It's upper limit, so we use b. Zero to b ax e to the 2x. Oh, if this is x squared, that would be a lot better. Just substitution. Now it is 2x, so this is iteration by parts, right? Differentiate, integrated. Right, the ax is going to be u to be differentiated 8 and then 0. Then e to the 2x is the other one to be integrated. E to 2x integral 1 over 2 and then integral again 1 over 4. Right, diagonal plus diagonal minus. Alright, so that integral give us ax times 1/2 e to the 2x, subtract 8 times 1/4 e to the 2x go from 0 to b. Right, we simply find the ax divided by 2, that's 4x, e to the 2x, and then 8 and 1/4, that will be 2, e to the 2x, go from 0 to b. And now substitute b into this. Right, first substitute b for b e to 2b minus 2 e to the 2b. Subtract 4 times 0 e to the 2 times 0 minus 2 e times 2 times 0. Right, now let's simplify just a little bit. For b e to 2b minus 2 e to the 2b minus this is 0 times anything, so that one gone, minus a negative, that's a plus 2 e to 0 power, e to 0 power is 1, so this is 2. Right, now this is e to the 2b, b go to infinity, exponential function, so this go to infinity and this go to infinity as well. And they'll say, what happened if we have infinity and then minus infinity? What is infinity minus infinity? Well, infinity minus infinity is indeed indeterminate, so we don't know what it is. Well, not quite on this one. This was, by the way, is 2. But this one actually is not indeterminate. If we rewrite this one bit like this, both of them have e to the 2b. If we factor it out, here we have 4b minus 2 plus 2. Now, see again, e to the 2b, that goes to infinity. When b goes to infinity, b goes to infinity, so 4b to infinity. Infinity times infinity is infinity. Plus 2 is still infinity. So that's why this one goes to infinity. Right? We factor it out. The 2 here is finite. Infinity minus a constant is going to be infinity times infinity is infinity. Plus 2 still infinity. So if it's infinity, we say this is divergent. Right, so that is that one. Right, next we have this problem. Now, this is a real problem. Of course, both negative infinity and infinity, so we have to split this in two. So first, let's split that at 0. X cubed e to negative x to the 4. Unlike the last problem, when we see this e to x to negative 4, we cannot integrate that. So integration by parts will not work. This one is a substitution, because u equal to x to the 4th, derivative x cubed will cancel nicely with this x cubed. Right, so the first thing we do is just split at 0. So let this be the first integral, and this is the second integral. Now we do for both of them. Unless of course if the first one is divergent, then we just want to stop and we say it's going to be divergent. If we have infinity plus infinity, infinity plus anything, unless infinity subtract infinity, that's different story. Anyway, let's do the first one. For this one, lower limit at negative infinity, so I replace that by a x cubed e to negative x to the fourth dx. Of course, like I mentioned before, this is a substitution. U equal to negative x to the fourth, so du negative 4x cubed, and then dx are multiplied here and divide by negative 4x cubed is dx. Right, the limits go from a to 0 . Right. So when x equal to a, u is negative a to the fourth, and x equal to 0, 0 to the fourth is still 0. Right. Right, divide the page into 2. Right, this integral equal to, I still have the limit. The limit changes to negative 8, from a to 0, so negative a to the fourth to 0. Right, x cubed e to the u dx is du over negative 4x cubed. Take out the negative 4. Negative 4 at the bottom. X cubed cancel out. We just have e to the u du. Right. Yeah, negative 4 at the bottom moved out, still at the bottom. Negative 1 over 4 e to the u is still e to the u from negative a to the fourth, 0. Now substitute in the limit. Right. Negative 1 over 4 e to the 0, subtract negative 1 over 4 e to the, substitute that in for u, negative 8 to the 4th. Now e to 0 power is 1. Now a go to infinity, so this go to infinity with the negative, so e to negative infinity is equal to 0. Remember, exponential function going like this, so when it go to negative infinity is equal to 0, so that one gone. All we have is just negative 1 over 4. Right, so that's just I1. Now we do for I2. That will be upper limit. Go from 0 to B. X cubed e to the negative x to the fourth dx. Right, substitution. Let u be negative x to the fourth. Same thing, I'll just skip that step and we say du is equal to du over negative 4x cubed is dx. Pretty much the same substitution. And x equal to 0, u equal to negative 0 to the fourth, x equal to b, u equal to negative b to the fourth power. Right, we go from the new limit 0 to b, 0 to negative b to the fourth power. Right, I will still have x cubed and e to negative x to the fourth, that is u, and dx is this. Cancel the x cubed, take down the negative 1 over negative 4 at the bottom. Integral of e to the u du. Right, 0 b to negative b to the fourth. Right, substitute. Negative 1 over 4 e to the u, which is negative b to the fourth. Subtract negative 1 over 4 e to the 0. Right, so again b go to infinity, so negative infinity, and e to negative infinity is 0. So we just have this negative negative, that's 1 over 4, e to 0 power is 1. So again we have this is 1 over 4. Right, so finally when we substitute back in, this is negative 1 over 4 and 1 over 4. I'll give us 0. Right, so let's just evaluate this again. This might not work well because we have both of infinity here, but let's try. It probably will give us an error here. The problem is because we have e to negative x to negative 4. That might be a problem. We'll see. Right, so that's good. Right, next we have this one as improper integral. Now, the limits are fine. We don't have infinity anymore. So what's wrong with this? Well, what's wrong is that when x equal to 0, then that is undefined, and we cannot have that. Right? So the problem is at 0. So let's draw the integral. Draw the integral. The interval of -1 to 27. The problem is it cannot be 0. So it cannot be 0. On the left of 0 is fine, on the right 0 is fine. So bottom line is we have to split this into one of them up to 0 on the left side, and from 0 on the right side to 27. So we have to split the integral into that case, that to avoid the 0. So I will say from -1 to 0 from the left hand side, because that from the -1 go to 0, that on the left side. We cannot have 0, so that's why we split at 0. I will rewrite this and put delta x on the back. And then from 0 plus all the way to 27. And we have 1 over x to the 2/3 dx. So we have two improper integral. We split in two. Of course, when we see this, we have to put the limit into it. Right. Let's call that is integral 1, and this is integral 2. We're going to do both of them. First integral, that on the upper limit, so let's say b go to 0. I will rewrite as x to the -2/3 dx. We go from -1 to b. Right. Now integral of that is just simple power rule. X to the 1/3 over 1/3. Going from -1 to b. Right, divide by 1/3 is multiplied by 3. I substitute b in and substitute -1 in. And then substitute -1. Yes. Now to the rest is easy. 0 here, 0 to 1/3 is 0. -1 to the 1/3 is -1. So this is, we have 0 for that, -3 times -1. So this is +3. Of course, we can confirm that. Let's see if it works. I'm just going to say from -1 to 0. And here we have x to the -2/3. That may give us an error. While we wait on that, let's just go to the next one. Now we have the lower limit, so let that be a. Right, so that's the problem with it. So let's just change, so that's why we need to change a very small number, right? Right, let's try that instead. Right, the lower limit is a. Right, so we have the values. Well, it's not 3 yet, but it's close. How about closer to 0? Right, let it run a minute. Right, so this time the lower limit is a. Go to 27. We still have x to negative 2 over 3 dx. Right, so most of this are still the same. Integral, we're just going to say 3x to the 1/3. Of course, that's the same thing. We don't have to write this step. X to the 1/3. Oh, sure, it's closer to 3, as you see on the calculator, which is good. All right, go from a to 27. Now I'm going to put 27 in for x and subtract 3, 0 to the 1/3. That's 1 0, 27 to the 1/3. By the way, the negative 1 to the 1/3, if you enter that in the calculator, make sure you have the parentheses. Right? So 27 to the 1/3 is cube root of 27, which is 3. So 3 times 3, 27. Sorry. 3 times 3 is 9. And that is 0. Right. So we have 9 for I2 and 3 for I1. Add them up, we have 3 plus 9, 12. Right, now, of course, we can also check. Again, we go from 0 plus to 27, and then x to the negative 2/3, and negative 1/3, sorry. Negative 2/3. What do we have there? Right. Should get close to 9. Right, close enough to 9. So add them up, 3 and 9, it's going to be 12. By the way, if we enter this from the beginning, it will give us an error for sure. For negative 1 to 27. I would be very surprised if they give me 12. Right, just so we have a last problem on this one. But when I make a problem, I thought I have more problem where we have the problem with the unbound integrand. So there's a problem with the function inside. We don't have a lot of that, so I'm just make up one here. So let's look at this problem. So just an extra problem, if you will. Right, we have this. So of course we can just write that, but that is just the sine inverse. So again, we see the calculator show that there's something wrong with it. So that's why we have to split the integral like this, because the problem with 0 in the middle. So we have to split to avoid the 0 from the left side, 0 from the right side, and do two integral like that. Now, what's the problem with this? Once again, if we divide 0, and that would be a problem. So we cannot divide by 0. That's first thing. So that is the problem when x go to 3. 3 squared is 9, 9 minus 9 is 0. So that's the problem at 9. So on the interval from 0 to 3, everything else is fine except we cannot have 3. So that means the integral we're talking about is in this interval, and this is only on the left side of 3. So we go from 0 to 3, negative sign, like that. Alright, so first this is equal to 0, and it go to negative 3 on the negative side. I will rewrite this as 3 squared minus x squared. I put the x on the back. Alright, like that, so we can use the sine inverse. That's all. But first, that's simple. The 3 to negative sign, so we have to use the limit for that. The upper limit to use b. Right, so integral of that is sine inverse of u over a. Where's the limit? Right, sine inverse of u is x over a. Going from 0 to b. Right, so just that. Now to substitute the limits. Fundamental theorem of calculus. Sine inverse of b over 3 subtract sine inverse, put in 0 over 3. Right, now the sine inverse. The good thing about sine inverse, if we graph sine inverse, that is sine inverse of x. I should only go from negative 1 to 1. So when put 3 in here, we have sine inverse of 1. Right, actually that is pi over 2. If we want to make sure go to degree when we do the inverse, that will be 90 degrees. We show is pi over 2. Right. But for most of other cases, we keep the calculator in the radian mode. So sine pi with sine inverse of 1 is pi over 2, and sine inverse of 0 is 0. So this is pi over 2 minus 0, which is pi over 2. Right. I thought I'd just add one more problem, because we don't have a lot of problem that has the problem with the integrand. Right. So make sure that whenever we evaluate the function, they have to be defined. So if it's undefined, we cannot do that. So we skip that values by writing, in this case, it is the left side of 3. So we use that notation. And then at the end, that's what we have. Right, with that, I stop this review right here. See you in another video in Calculus 2 review. Thank you for watching.